So let me start with discussing what tabular data is. So tabular data is everywhere. Tabular data is defined by organization in rows, columns. We can find it in spreadsheets, in databases, in general tables of data, and this is the general organization. You can understand that in rows, we have measurements or observations or objects, and then in the columns, we have variables or properties about those objects or observations. Typically, we will have just a few or a moderate number of columns, but the number of rows can be huge. So these large amounts of data can be handled efficiently by making use of homogeneity of types in the columns. So typically, we will have all the elements in one column being categorical data or numbers or dates or some other things. And some of the elements can be missing. So Wolfram language 14.2, released just a few weeks ago, introduces a new data container which specializes in this type of data, and it's appropriately called tabular. There are many ways in which you can construct a tabular object, and you will see them during these talks, but probably the simplest one is simply providing a matrix of rows and columns in the first argument of tabular, and then in the second argument, you give the names of the columns. And there you have your first tabular. So notice that we have some indications of types. So this is an indication of being a column of strings. And then we have a tooltip. So for example, this is a column of integers in 64 bits, or this is a column of dates with date granularity. So the standard workflow with tabular is represented here. So Wolfram language 14.2 already adds more than 30 new functions to work with tabular, and the traditional structural functions of the language have been updated to work with tabular too. Tabular already offers nice visuals, and in future versions of the language, we will improve on that. There is extensive documentation already, right? So this is a tabular guide for tabular, in which we have various sections and the functionality about tabular. And we have also added examples of data in the Wolfram data repository. And here, let me share with you this again. So here you have various data sets that will be used during this talk. Okay, so as I was saying, this is the general workflow. The key idea is to go through several steps, communicating always using tabulars. These are the tabular objects. And so we will start with getting data sources, cleaning them, then understanding what you have by a process of transforming the data, visualizing, modeling, and then you can communicate the results. So let's describe here some tabular basics. So again, let's construct a tabular. Now it's going to be a little bit bigger. So here I have data about the G10 countries, which are actually 11. And we have this matrix of 11 rows and 6 columns. And we have the column keys, which are these 6 column keys. So this is the tabular we have, right? And you see again how we have different types. This is a column of entities. This is a column of expressions, which are these images. This is a column of strings, a column of quantities, with magnitudes being reals and the units being square miles. So this is population, and these are dates, the date of independence of each of these countries. So once you have one of these tabular objects, you can extract individual entries, as usual in the Wolfram language, using the part language. For example, this is the area column of the first row. So we are referring to the area of Belgium. So here we have the area of the last row, which is the United States. We can extract a whole row, and to do that, we return the data as a new object called a tabular row, which can be normalized into an association with the various keys used for the column headers and the entries of the corresponding row. We can also extract a column, and we return the result as a tabular column. A tabular column is the object that contains a type. So this is the type. It has 11 elements, And this is telling us that none of the elements of the column is missing. We can also normalize it, and we get a list of quantities. We can also normalize the whole tabular, and we get a list of rows, meaning a list of associations. Okay, so this is about extraction. Now, some of the basic properties of the tabular object are its keys, the keys that we introduced here. That's a list of strings in this case, or the types. If we call column types, we get an association of the type associated to each of the columns. So again, entities of country domain, expressions, strings, quantities, etc. Let's continue with basics. So let's take again our G11 tabular object. So now, how do we add a new column? For example, we are going to add a new column called density, computed from two other columns, population and area, right? So we just divide the population by area. So we do this, and we see that we have added a new column here. It's a quantity column, of course, with proper units, peoples per square mile. And it was added at the end by default. Here, we will use the same function, transform columns, to do several things. First, we specify that we want the new density column after the capital column. We use this, some sort of anchor column, to place the other one. Then we say, okay, the population is going to be changed. Notice that this is a new column, but this existed already. So this is going to change the population column. We are just going to numerize it. We are going to apply n. So we are going to change from integers to reals. And finally, we are going to remove the independence column. So you see, here we evaluated this. We got the new column, place where we asked for. Population changed from being integers to being reals, and the independence columns has disappeared. I wanted to mention here that Tabular specializes in the 2D rectangular case. We always had in Wolfram language, or for many years, another data container called dataset, which specializes on more general hierarchical, possibly rugged data. And dataset treats all levels in the same way, while Tabular, you have seen that it treats rows and columns in a different way, right? It requires homogeneity of type in columns. So, for example, take again our 3 rows of our tabular object. We can convert it into a data set, and we can convert it back, right? And so this shows that for the common case, the rectangular 2-dimensional case, they can work both together, and they can convert into each other. Okay, let's look more about types. For example, let's look about numeric types. So here we have a tabular with a column of integers, a column of reals, and a column of numeric expressions. Notice that we also have a missing object here. And if we ask for types, we see that the presence of a missing object didn't spoil the automatic choice of types. So this column is still recognized as a column of reals. We can now say, I want to convert my column of integers in 64 bits to column of integers in 34 bits, right? And so there is this function in general to change the types of a column. Let's do also examples with dates. For example, let's take 100,000 random dates in this year. If we take the date 50,000, we get that one, which was randomly generated. We can insert all those dates into a tabular column. And of course, if we extract the date number 50,000, we get the same one, right? Again, same language of part in Wolfram language. Now, tabular column is a lot more efficient in representation, and Tabular takes advantage of that. For example, you see our dates were originally a list of 36 megabytes, while tabular column stores the same dates in less than 1 megabyte. Computations are also faster. For example, if we compute the mean dates, we get that one. If we do the same computation with tabular columns, it's a lot faster, many orders of magnitude faster. For example, we can now insert 30,000 missing entries at random positions into that list. We put that new list in tabular column. You see, because there were many repetitions in this random integer list of positions, we get this number of missing entries. And now we can still do the computations, and min will not get confused by the presence of missings. It will just ignore them and do the min on the non-missing values. Tabular is very, and tabular column is very efficient in the dealing with types, and it can handle all the all the numeric types of the Wolfram compiler, which are all of these, and then several other types of the compiler, plus other ones that have been added specifically for tabulars, like dates or entities, etc. So there are many types that it can take advantage, and in the future we will add more. Finally, I will end up with the last slide showing an example of working with a large tabular. Here I have a file of 600 megabytes downloaded from NASA. It's a file about asteroids. And import takes about 2 seconds in downloading it. You see that the file is represented even with a smaller size. This file has 720,000 rows with 80 properties. And this is the tabular that we get. Notice that the original was a CSV file, all with strings, and the import of this object already assigned proper types to all these columns: strings, numbers, reals, integers, even dates. A nice way of getting an idea of the structure of some very large tabular object is using the function tabular structure. For example, here we will have in this column, we will have the column keys, and here we'll have some of the properties that we may be interested in, like the type, like how many elements are not missing, how many are missing. Some columns are completely missing, and then we associate to them type null. And here we have the byte count. We can restrict, for example, to the columns that start with letter E. So we get these. Or we can ask for specific properties, which are documented in the ref page. For example, there is one called count distinct that will tell you how many values of these 720,000 are actually distinct. In this case, for example, eccentricity of the asteroids are all different, but the epoch dates used for representation of orbital elements, you see there are only a few values. We can take advantage of that by categorizing, which means just store the different values and use an index as value for those columns. And then this shows that by just categorizing one of the columns, the column epoch, this one with 3 elements, we have gained 5 megabytes. So you see how by categorizing other columns, we could gain a lot of space, a lot of memory. Okay, so this was a quick example and a way to show that we can handle really large tabular objects.